Okay, thank you very much for the kind invitation, and I want really to thank the organizer and all of you for being here until the very last day of the very last talk of the this beautiful workshop. So today I'm going to speak. Well, I'm following this trend of no-go theorems and about objectivity based on Wigner's-Friend paradox. However, I would like to go a bit into the very concept of the tool of no-go theorem as an investigation, motivated also by several conversations I had with both philosophers of physics and prominent quantum physicists, and we seem to disagree on certain stance. And in particular, I would like to say something which is very trivial for in our community, but still I would like to reassess the no-go theorem as I said, as a tool of investigation for fundamental research, and see how this is applied in the context of Wigner's-Friend scenarios. And in particular, I will go into a debate that has going on through the last few months. Bruckner's theorem that we have heard extensively in the last 2 days, that was criticized to some extent by Richard Healy, and who proposed an alternative argument that I will expose here, and propose our counter reply to that we have recently submitted. So quantum theory, as we have seen in this workshop, and as we all know, addresses certain concepts that are very philosophical. And the way we have found in the modern foundations of quantum physics to address this problem is principally the way of formulating no-go theorems. So ruling out, formulating in a certain decidable way certain statements, and then finding theorems that rule out, that falsify this statement. However, what I want to point out is that there are two different phases of no-go theorems. So how a no-go theorem goes, one postulates a certain set of assumptions from which one deduces logically a certain decidable statement. If one then formulates a theory in which the statement is false, the falsity is transmitted back into the assumption through modus tollens, the tables of classical logic. A no-go theorem follows that the conjunction, so one or more of the assumptions cannot be held within the theory T. However, this is mathematics only. All I have said here has nothing to do whatsoever in principle with physics. If the assumptions are physically motivated, and especially if the statement is experimentally falsified, then we learn something new which is about physics. So in Feynman's word, scientific method is based on the principle that observation is the judge of whether something is so or not. Observation is the ultimate and final judge of the truth of an idea. So the no-go theorem in this sense reads something like, nature violates the conjunction of the assumption. So we have gained a new empirical content, whereas in the mathematical case, this is basically true. The whole power of the theorem is already contained within the assumption themselves, and is only the theory that we devise that can conform to this or otherwise. So what we should strive for is for having empirical content into our physical and in general natural scientific theories. In the words of Max Jammer, following the development of a critical empiricism of the Vienna Circle in practice, our theories are formed by two different sets of statements. The formalism, which represent the logical skeleton of a theory, is a deductive and axiomatized calculus. We also have then the physical part of the theory, which is a hypothetical deductive system of empirical statements. Empirical meaning what I've said before, that can be actually checked, interrogating nature about this. And we need a set of rules of correspondence or operational rules that are relating what the symbols of the theory represent to what we can actually do in the lab and to pose our questions in an empirical way. Max Jammer would conclude that the formalism without the rules of correspondence is a meaningless game of symbols in the context of physics, of course. Bell's inequalities that have opened to some extent this systematic research and foundation based on no-go theorems can be therefore stated as some initial postulates: freedom of choice and local realism. We all know what formally these mean. And from that, a decidable statement can be formulated. The very quantum formalism violates this statement. So even if we were not able to perform any experiment, and if we're not able to build anything that was likely resembling quantum, also Box's word would violate this thing. So this is not related to the empirical content of our theories. This is related to a certain consistent formalism that we have created, and then we can demonstrate that within theoretical apparatus or system, this statement doesn't hold always. So the no-go theorem, in the sense of Bell's, has a mathematical formulation has a mathematical content, that the formalist does not conform to this. Of course, the formalism is in its turn motivated by certain observation and has been formulated to resemble a certain, and to be consistent with our observations. But to test the theory is not enough to just formulate a theorem. So mathematics again. Whereas it also has, if real experiments also violate no-go theorem, as we have recently demonstrated in loophole-free, people have recently performed the first loophole-free tests of Bell's inequalities, real experiment violates, therefore nature violates the conjunction of Bell's theorem. Okay, we have seen that in recent years, the problem of Wigner's friend has been addressed from the point of view of these no-go theorems. Charles Love in 2015 and then a restatement in 2018. Forchiger and Renner. And more recently, Richard Healy, following what I've called this theorem, Pusey-Mazanes, Leifer-Healy. I don't know. There are several people who have conformed to this kind of argument, which is very similar to Bruckner's one, but has certain differences that I'm gonna now, in the second part of my talk, to expand in detail. Okay, we've seen, I will go very fast here because I think by this time we all know very well, but there are a certain set of assumptions, A1 to A3, and this set of assumptions through a certain deductive, a certain series of inferences, there are deductive inferences, we show that they lead to contradiction, therefore a theorem can be formulated that no theorem based on this assumption can actually hold. This is the mathematical part of no-go theorem. What I want to say here is that we should remain focused on the fact that our proposed Gedanken experiments, also in the context of Wigner's friend, they should be rooted in our empirical evidences and in the possibility, at least in principle, of adding some empirical content to the no-go theorem. So it's not enough to have a consistency check. It's not enough that these theorems, despite they are very far away from the technological domain that we can actually implement today, we should at least be able to give them the possibility in principle while technology develops enough to get to that point. So even if we are entering something very speculative, we should always have in mind that these should be, in principle, testable statements if we want to rely on no-go theorems and add some empirical content to our no-go theorem. This is the no-go theorem of Chaslev, so no-go theorem for facts of the word, which is based on universality of quantum theory, facts of the word, locality, and freedom of choice. What I believe is that, and this came about yesterday during Chaslev's talk, is that locality and freedom of choice need to be added to the no-go theorem only for the empirical content. So only in the case that one actually wants to test and to propose an actual way to test the no-go theorem, one has to add these other two. In fact, formulated in the way that Chazov proposed yesterday, so based on the marginal problem, and then formulate a fine theorem. If you look at the original Fine's theorem, this is not assuming whatsoever space-time structure or non-locality, or locality in the assumption. So the marginal problem is actually a problem that is formulated only for probabilistic theory and then motivated on certain physical assumption. One has to impose constraint to these probabilities, and it's at that point that one introduces locality and freedom of choice, because if one wants to actually perform an experiment, then one has to put up additional assumptions. So, for testing the no-go theorem, as I said, I will go very quickly through this formal part. We have seen this already. But for testing the no-go theorem, we need to give the external observer the freedom of choice to perform one or the other measurement. And these two measurements should be realized independent from each other's outcome. So we require that they occur in space-like separation also. From this, one can formulate an inequality, but the inequality in this sense, although we cannot actually practically implement these experiments, this inequality has an empirical meaning, because we have a set we have a protocol of operations that can actually be done, given that we will reach a point when we can build an observer in quantum superposition. I put this also here because I hope to stimulate some debate on whether. So it was this month, I think, Proietti et al. They performed actually an experiment claiming to have demonstrated experimentally Bruckner's theorem. And in this case, the observer is a photon which gets entangled with the original entangled pair. And Rovelli showed this, we discussed this at the APS meeting, and for him this was a great achievement because it was corroborating his view of quantum theory that every interaction can be seen as a measurement. And so here the question is this actually testing the Bruckner's theorem? But the broader question is a photon enough what is the minimal requirement to consider an observer in these conditions? Okay, so Healy's criticism Healy criticized Bruckner's theorem to the extent that in order to test this inequality, Alice and Bob have to choose in every run which measurement to perform. And Healy says, okay, but when a measurement is not performed, so when the two Wigners are measuring the same direction of the friend inside, the measurement along the other direction is not performed. So since not in every run all the possible outcomes are there to be realized, this is weakening a lot the theorem, because you don't have in a single run of the experiment, you don't have the possibility of observing all the outcomes. There is only one of the four possible settings where all the outcomes are present in the experiment. And he comments, and I stress this fact because I think that this is something that can be actually sent back to Healy as a criticism, that the outcome pairs are not epistemically accessible by any observer, including the four agents named in this scenario. And so their statistics are of no scientific interest. This is from his paper. So Chazov has shown yesterday his reply that since there exists one configuration where the outcome can in principle be realized, one can extend this to the fact that in every other setting one assumes that the outcome would exist, even if they cannot be measured. And what Healy proposed is to revise the theorem. So the theorem has basically the same conclusions on weakening the objectivity of the outcomes. However, he proposes a slightly revised version of the argument to address this criticism of not having all the possible outcomes available during the protocol. So I take the responsibility for these assumptions. They're not present in his paper. The assumptions are basically definite outcomes. This is defined by Healy, so this is a quotation. Every measurement has definite physical outcome registered, recorded, and experienced by an experimenter. He also needs quantum universal validity of unitary quantum physics, because he's, of course, like in any other Wigner's friend experiment, is treating the observers in the box as quantum systems. And he requires, I put this in parentheses because for his argument it's necessary to have non-absolute simultaneity, so he has to switch from one another reference frame. So the setting is more or less the same as Bruckner's theorem. There are the two internal observers and two super observers or Wigners outside, and they all perform a spin measurement on the same entangled, and the third pair, which has been generated as an entangled state. And from these, he shows that a Bell's inequality follows in the normal way, where E are the correlation between the observed outcome of A, B, C, and D. He then goes to see whether quantum mechanics violates this inequality, trying to get around the criticism that he addressed towards Bruckner's theorem. The protocol that he proposes is the following. So he described this from the perspective of Alice. Here, on this player is describing a protocol in the following step. There is a state preparation. Then Charlie measures applying a unitary evolution to the initial state. Charlie is the player which stays inside Alice's box. Then Debbie measures the other friend. Then Alice undoes Charlie's measurement, applying the inverse of this unitary measurement. Then Alice measures, Bob's undoes Debbie's measurements, and his turn to measure as well. In short, after both the friends have measured, there is in principle the possibility of calculating the correlation function between the two outcomes. After one of the two have been undone and one of the Wigner has performed a measurement, this correlation function is well posed. And eventually, when the other one has been erased, A and B can, the two super observer can actually now compute correlation function. However, one correlation function is missing. Only three of them can be computed in this sense. So what Healy does is to make the two labs moving with constant velocity and going in opposite directions. And this allows him to change the reference frame and to compute the last and fourth correlation function in another reference frame. In this reference frame, which is the one from below from the bottom to the top in red lines, you see that in this case, the measurements occur in different order. In this sense, he requires that the two event happens in a space-like separation, but not for the assumption of locality. And he then performs a D measurement, C measurement, D is undone, B measures, and at this point, since C outcome still exists and B outcome now exists, there is this region of space-time where the two actually occur, where the two outcomes exist and where the correlation function can be computed. So his main claim, the merit that he gives to the argument, and I understand, is that there exists, okay, there should be a bit stronger color, but there exist four regions of space-time. This place here where CD exists, these two stripes here where the outcome exists, yet only in two different reference frames, never in the same, and these are the region where both outcome of A and B exist.
You're saying it exists even if it's only in that reference frame? I mean,
he says.
That's not very relativistic, right?
He has a weird definition of exists.
Sorry?
He has a weird definition of exists.
Okay. So instantaneously, if in some reference frame it exists everywhere, that's totally non-relativistic.
Right.
Anti-relativistic.
Yeah, the fact what I was trying to point out since the beginning is that not having any operational.
Good.
Yeah. Without operational meaning, this quantity can be defined in this sense they exist. They can be defined unambiguously, but we don't know to what they would correspond if you make them, how to measure them, basically. Yeah. So now I come to the problems. Yeah. So the argument is not testable in principle. That's the first problem. And Healy is fine with this. He affirms that the circumstances of the Gedanken experiment are so extreme as forever to resist experimental realization. Yeah.
Why again? I must have missed something. Why is it so extreme as to be untestable?
Because the two wings are in space-like separation. So they can't. So even although you may say the outcomes exist, they can't get together and compare them.
Yeah.
Before the undoing happens, and then it's gone.
Yes. Isn't that why do they have to be moving to do that?
Moving to allow him to compute a fourth correlation function.
But isn't that just a standard assumption in a?
They don't have to be moving. The moving thing is a side point. The point is there exist reference frames in which those things.
Right, but isn't that just a general assumption in a standard Bell model? They have to be space-like separated.
Yes, but
Yeah, for different reasons though. Yeah. So since
in the Bell experiment, yeah, the measurements aren't undone.
yeah, but the experiment. This is not an experiment. That's the point. So
It's the undoing.
yeah, it's the undoing part. That when the undoing happen, these matter. So if you
Okay, so never mind. I got it.
if first is undone, D is undone, and then C is undone, is different than the other way around, and this allows Healy to claim that one correlation function can be computed and the other cannot. This step can be of course criticized, like combining correlation function computing in different reference frames. And as third, if the measurements are actually performed, there is no violation of Bell's inequality. So if you actually apply the measurement in the sense of not unitarily evolving but collecting the statistics, you will not get to a violation. A possible solution, though, is to adapt the protocol to a testable one. So to actually give an operational meaning to this protocol, and this is what we have proposed. So I've said already, there is no single observer in the universe that can actually collect any of these correlation functions altogether to compute eventually and see whether the violation occurs. This is the non-testability in principle. If one accepts to use correlation functions coming from different reference frames, then one has to justify why he's taking these particular ones and not others. For instance, let's say that you compute which one I have, BC in the other reference frame this time. Instead of, so he was computing these in Bob's reference frame. Let's try to compute this in Alice's reference frame. You will see that in Alice's reference frame, between T1 and, no, here we are, between T1 and T3, sorry, the outcome B has not yet been realized. So the state of B is just an empty register. Whereas C has been realized with probability 1/2 for the outcome plus or minus 1. Whereas in the second part, C is erased and B has been realized. So they never exist at the same time, which leads to a computer correlation function that gives us a result 0. The same can be said for the results AD computed in the reference frame of Bob. And therefore, if one decides to combine this correlation function computed into two different reference frames, then one gets AAB plus 0 plus ECD minus 0, which always satisfies Bell's inequalities.
You should have done a Lorentz rotation, though.
Sorry?
You should have done a Lorentz rotation rather than a Euclidean rotation.
So the proposed solution would be that super observers, Alice and Bob, now are allowed to actually decide which of the two outcomes which of the measurement to perform, sorry. So Alice either measures A, so her own actual, as prescribed by Healy, or she can decide to get the actual outcome occurred inside her box. So either she measures her own direction, or she opens the box and asks the friend which is the outcome. This allows to give an operational meaning, because in the choice where they both, Alice and Bob both measure along their direction, there will be an actual possibility for both of them to collect statistic at the end. When B and C, when Alice measures and Bob decides to not to measure but to actually collect the outcome from his friend, then there will be the possibility of establishing BC. In the same way, one can establish AD, and eventually, if both Alice and Bob collect only the data from their friend without performing any further measurement, they can both collect statistics on CD. However, the conclusion is that, in this sense, the argument of Healy becomes virtually equivalent to Bruckner's one, because there is no single run of the experiment where all the outcomes can actually be present. So there is a modified version that makes it, giving the freedom of choice and the locality, these are necessary conditions for the testability of the experiment. Imposing them doesn't require any more to change reference frame, but it weakens to some extent the result that one has to further postulate the fact that even in the runs where all the outcomes are not present, since there exists at least one, they have existed also in the other ones. And I think that's all. Thank you.
So the obvious question then for me would be, okay, so if you can create a modified version of Healy's that essentially makes it equivalent to Bruckner's,
Yeah.
then that doesn't surprise me at all, because it's if they're moving away from each other, they're still assumed to be inertial, right? So, because they're moving at a constant velocity, right?
Yeah, I mean, yes.
Right. Okay. Could you do the same thing if there was an acceleration, a relative acceleration?
Okay.
I think that's an important question.
Yeah.
I don't think it's trivial.
Right.
I know that. I know
But this is
that,
your paper. Whereas it's said is I mean.
Yeah, but that's not a whatever. But the point is I think it's an important point, right? I think it's and I understand Chaslov's argument, and I'm willing to buy it. I think.
Yeah.
But nevertheless.
No, I didn't want to dismiss because of your paper. I wanted to say that you have good reasons to believe that it's problematic in accelerated. I don't know.
I know you don't know.
Yeah.
Just put it up in the archive.
I don't know. Yeah,
it's something to think about.
Yeah. I don't know why this should be problematic. I mean, they can stop. I mean, the fact that there are some instances where this is not violated, like if they are accelerated, the entanglement is degraded. This would allow would not allow them to violate a Bell's inequality. But even if they don't take an entangled state from the beginning in the first place, they will not violate it.
No, but it's the same state, right? It's the same state that violates it in one setting, but you switch coordinates and it doesn't in the other coordinate system. It's the same state. It's not a.
Yeah, but they can stop. I mean, they decided to move or not. Why are they bounded to accelerate forever? That's the make, right?
Oh well, because if you pass one past a horizon, say a black hole, event horizon, then you're stuck.
Sure. But not all the entangled pairs are the one that's passing the horizon.
True.
So there will be in the universe entangled pairs which are not in
Right,
relative
and this
acceleration, and these are enough to violate the
This
system.
goes back to
certain
the
instances.
sufficiency question. Is it sufficient that it just violates it once?
Yeah, in that sense, yes. That may understand.
I mean, I think the whole moving thing is a bit of a distraction. I can think of the description of an experiment in different reference frames, regardless of whether there's anybody stationary in that reference frame. So Healy wants whoever it is, Charlie and Debbie, to be stationary in the reference frame you're analysing it in, but there's no reason. There's no reason for that.
The problem is there is no experiment. Everything is unitary, and we know that the state is not a relativistic invariant notion because of relativity, simultaneity. Therefore, the correlation functions are not calculated correlation function, not relativistic invariant. That's why you can choose whatever you want, and that's Flavio showed, you can choose such planes that there is no violation or there is violation. The only way to fix this is to perform an experiment. And then the data are relativistic invariant things. But when you do it,
So the state isn't relativistically invariant, but the predictions are, generally speaking.
predictions for the measurements.
What
For the performed
predictions are?
measurements.
Well, look, if I have two spin-half particles that are entangled and I go to another reference frame, they may no longer be entangled, but something else is, like the positions of momentum. It changes which degrees of freedom correspond to which other degrees of freedom in different reference frames are different. But if I make a measurement of the spin in this reference frame, and I translate into another reference frame, and I transform both the states and the operators, then I'm going to get the same predictions.
So this is a common confusion that people just looking at a spin degree of freedom in a relativistic setting, which is simply not an invariant concept. So the only way to do this is to look at space-time locality in the sense of field theory, and then there's absolutely no question that changing coordinates will change anything in the basic locality set.
The only thing that changes are what we think about. Like if I make the measurement in one reference frame at t equal constant, which we usually do for the intended state, then the other reference frame, this will be shifted in, but this will be the results, and the correlations will be the same.
It will be sitting somehow in the combination of translational and spin degrees of freedom. It will be exactly the same thing. So
That's
so
generally
it's
true.
just silly to look only at the spin.
But that's generally true for inertial frames. That's not always true for non-inertial frames. Like,
No, this is.
there's not a symmetry for non-inertial
So there are
frames.
two effects. One is entangling of momentum and spin. But even without that, let's say, it's just relativity simultaneity, that what we call the measurement, like entanglement, is the testing of correlations at t equal constant. The other guy will not even call this as a test of entanglement, because for the other guy, these two events will not happen at t equal constant, but one will be shifted at later time. Nevertheless, are the correlations that will be observed the same in both cases? And that's what is relative invariant. But for that, you have really to make an experiment.
The accelerated stuff is more tricky. You have to actually make models of the interaction. So the Ulrich effect is not a very simple thing.
I know. That's why I'm
Right.
because
So
I'm talking, and I'm
it's
talking
actually
specifically about the
an
Unruh effect. I'm not
accelerated
talking
lab
about
is a complicated thing because
Yeah.
the two ends of the lab, for example, move
Mhm.
away from each other.
yes,
So,
absolutely.
so
Which is why I think, but that's why I think I don't think it's something that is. I think it's something worth exploring because I don't think it's as simple as the inertial case.
Good. Shall we thank Flavio again and
yes.